Okay, this time up we're going to be looking at half-life. And as you can tell, it pretty much is what it says. It's the amount of time half of a radioactive sample takes to decay. And so if we started with like one, well, this is concentration in moles, but 1 mole of it, to get to the halfway point would take a certain amount of time. And so that times would be 1 half-life. Okay, 2 half-lives, it's going to reduce half by that, and then half again, and then half again, and then half again. Half-life, it reduces by half every time that time unit goes by. This is looking at it more in a mathematical formula. So I like this one because it uses A for amount, and little a of subscript O just means your initial amount. And so you have an initial amount multiplied by 1/2 to the time divided by the half-life power. And so it makes it a little complicated because you're doing things to a power, but that'll give you the amount that you're left with. Now you can rearrange this formula to get any one of these 4 variables, but I'll show you how to do that a little bit later because it can be a little bit tough, but we're in a place in high school where we don't need to avoid things just because they're tough. We need to be able to learn how to use them, including a logarithm. So first, some more intellectual facts. And so the half-life is unique to every element. In fact, every element has its own different half-life. Even some that we think are stable, they just have tremendously long, like trillions of years even, types of half-lives. Some of the other ones, like isotopes, for instance, carbon-14 is an isotope because carbon-12 is what we have on the periodic table. So carbon-14 would be an isotope. It has a half-life of 5,730 years. And we use this for fossil dating. Remember, that doesn't mean that it breaks down into nothing. It just goes through a beta decay, and so it ends up becoming nitrogen-14, which is pretty stable. So that's the great secret of half-life, is that it doesn't just break down, it goes through one of the decays we just learned about, and so it turns from a parent nuclei into a daughter nuclei as it decays. So that means you're getting rid of one of the substance, the parent nuclei, by half, and remember you can just reduce it by these numbers for every half-life that it goes through, but then you're going to increase the other one. So a lot of people start questioning how can carbon dating be accurate if you have no idea how much of carbon-14 was in there to begin with. Well, it's because of what it becomes. So since it becomes nitrogen-14, which is stable, we can look at the proportions of carbon, the parent, carbon-14, that parent nuclei or parent atom, compared to the amount of nitrogen-14. Now, there are some small variables, but for the most part, you can actually tell where it would fall on this time period based on the percentages that you have of both. It gives you an idea of totals then and the amount that it's converted into. All right, so now I want to look at 2 examples so I can show you how to mathematically solve for different things in this. We're going to start with these 2 problems. The half-life of potassium-14 is 10,000 years. If you started with 80 grams and now you have 10 grams, how old is the sample? So we're looking for the actual age of the sample. Then this one, 140 grams of nitrogen-15 decays to 35 grams in 30 years. How much is 1/2 of nitrogen-15? We're looking at the half-life of nitrogen-15. And we're going to use this equation. And notice we have 3 out of the 4 variables. And this one's set up to find final amount, but through simple algebra, we should be able to solve it for any of the variables in this equation. So don't get scared. I'm going to walk you through all the methods. Just hang with me. So first thing I need to do is I need to identify my variables that I do have. So in this first problem, potassium-40 is 10,000 years, the half-life of it. And so I can go ahead and put that down here. 10,000 years is our half-life. And then we started with 80 grams, and now we have 10, so the amount that we have now, and it wants to know how old, so it looks like we're looking for the time that has passed in order to get that amount. Now, down here, it says 140 grams of nitrogen-15, so that's the amount we're starting with, 140 grams. Decays to 35 grams, that's the amount that we would have remaining. In 30 years, that's the amount of time that's passed. So how much is one half-life? So we're actually looking for the half-life of nitrogen-15 for that second one. And then we have to start to play around with the equation. Now, what I'm going to show you is that when we have the variables that we need and the proper formula, we can solve for any of the variables that are remaining, even though it isn't set up for that. It's just simple algebra. And it might look a little confusing because I'm not going to do it by plugging the numbers in. You can if that really helps you, but I find that to be a bit of a crutch. Algebra is the simple way of moving something from one side to the other by using the opposite of whatever function it's currently being used in. So we're going to solve this for t, and I'm going to do it with you, so hang in there with me. The first thing I want to do is, since I'm trying to get t by itself, I'm going to try to get rid of AO on both sides. I see that it's being multiplied, so I'm going to divide both sides by AO. Now, since that means that this is all now being multiplied and divided by the same thing, it cancels out. And we can write this anew as now the final amount divided by the original amount is equal to 1/2 to the t divided by h power. Now, this is where it gets a little bit tricky because a lot of people don't know how to get rid of things being up in a power, especially when it's already a fraction up in a power, okay? So that's where you need a function called logarithm. And here's the thing. If you can do a logarithm base on a really fancy calculator, you could do a logarithm of 1/2 and simply reduce that down and move it over here to that side. Most of us don't have that. We have a log 10 button. And so that log 10 button will also work. We're just going to have to do basically both sides, because if you multiply both sides by something like a log, or take the log of both sides, it works out fine, all right? And so it's going to end up looking a little bit different. So let's write that in to where I did a log of this and a log of this, okay? In order to do that, I then get yet another equation, which is now log of, and let's move this up a little bit so we can see it a little bit better. Log of a divided by a original is equal to log of 1/2 times t divided by h. It's now times, okay? Because we pulled that out through the logarithm, which means we can just divide that side, or both sides, by log of 1/2. It'll cancel out over there. And then we do this side of log of 1/2. And we'll get yet another equation, which is the log of a over a original divided by log of 1/2 is equal to t divided by h. And we're trying to figure out t, so we still need to move that 1 over, which is just an opposite function. So we're going to multiply by h. That's going to do away there, and multiply this by h. And that will give us our final equation that we need, which is going to be h times the log of a divided by AO divided by the log of 1/2 equals t. And then we can go in and plug in our variables, okay? So let's do that. Let's go plug in variables, and I'm going to move this up just slightly more so we can see one more time here. Actually, I'm going to make this smaller if I can. All right, so I made it smaller, and I went ahead and plugged everything in. And as you can see, I just switch sides. So t is equal to h times log of a divided by AO divided by log of 1/2. And so you get 10,000 years times the log of 10 grams divided by 80 grams. And here's a little hint. There's dimensional analysis, meaning those grams would cancel each other out. And so it would just be a number divided by a number times 10,000 years. Well, all of this ends up equaling 3 if you plug it into your calculator correctly. 3 times 10,000 years is going to give me 30,000 years. And we know that that is the amount of time that has gone by. Okay, for the sake of time, I went ahead and started to solve some of this one out. For our second problem, you can see these were the variables we have. We were trying to find h. We start very much the same way, so we're going to move all of that around just like we did the last problem. The only difference is once we get to this point in our equation, now we're trying to solve for h, and h is on the bottom. Well, it's really simple. In order to move that over to the other side, we're going to have to multiply it to the other side and then divide everything on that side by that side. So essentially, these two are just going to switch places, everything on this side with the h. So if I do that, I'm going to, like I said, multiply by h. That gets rid of h. Multiply by h here. And then I'm going to divide both sides by all of this, okay? So to do that, I'm now going to get that h is equal to t divided by the log of a divided by AO divided by log of 1/2. And notice it is a little complicated, so you're going to want to put in all your parentheses. Now let's just plug in our numbers. So now that all of my numbers are in there, again, you can see grams cancel out, so this is just going to be in numbers. If you put all of this bottom portion in your calculator, you'll find out that it just equals 2. And so 30 years divided by 2 is 15 years. And that's going to be our half-life of nitrogen 15. That should all make plenty of sense too. Think about this naturally. If you've gone through 2 half-lives of 15 years is 30 years. And so let's just divide this by half twice. 140 divided in half once is 70, and half again is 35. And that brings us to the next thing. A lot of this is actually just common sense. So you can think this out and say element X has half-life of 1,000 years. What percentage left after 2,000 years? Well, that means it's gone through 2 of the half-lives for 2,000 years, right? Which means if I start with 100%, after one half-life I go to 50%, second I go to 25%. So I can just figure out what 25% of my original is, okay? You can do that for all of them as long as they're easy ones. The reason you need to know the formula is in case they're more difficult. I hope that helps.